Okay, I think I'll start. So we have a smaller group today. Some people are in New York.
Well, we're very lucky to have Irit.
Yes, thank you. So I thought I'd do some like a slightly like a teaching thing. Seeing that it's a topic that I'm not an expert on, but I got into it and I wanted to describe it a little more slowly. So I'm going to talk about approximate covers, and this has something to do with the algebraic topology. So we'll talk about covers and then relate them to cocycles, and then cocycle expansion, which is a kind of high-dimensional expansion, and then we'll see how it compares to spectral expansion. And then in the second part of the talk, I want to talk about how this I got interested in this because it relates to agreement tests, which are important in CPs, and you see how covers kind of show up naturally in that area. Okay, so let's start with simplicial complex. Is just, let's say, a family of sets that is downwards closed. So we have a set of vertices, and we have a collection of subsets of the vertices that whenever you have a subset, you have all the subsets of that subset. And I'm going to focus on most of the talk, well, half of the talk on two-dimensional simplicial complexes. So that would be just a graph with vertices and edges, and then we add another set that we call triangles, but these are just sets of three vertices, just like edges are sets of two vertices. Okay, so that's going to be my two-dimensional complex, simplicial complex. And I want to define what it is. What is a cover of such a thing? So let's start with a graph, a cover of a graph. If I have just a graph with vertices and edges, this is something we're more used to. Sometimes it's called a lift, even though it's not formally the correct term, but that's the term that's used in computer science. A lift usually comes with a number. So let's say, what is a two-lift? You have your graph G, a bunch of vertices and edges. And then your two-lift, you take every vertex and you duplicate it twice. Just put 2 copies for every vertex. And then for every edge, you put a matching. Either you put a matching like this, or you maybe, there's only 2 possibilities for a matching, and that's going to be a 2 cover for your graph. If it's a T cover, you just replace every vertex by T copies, and you put a matching on these T copies for every edge. So that's a T lift. And there's no restrictions. So you're just free to choose these matchings however you want. You get a T cover of your graph. And kind of the property that we are used to having for this thing is that locally around a vertex, if a vertex here had degree D, then each one of its copies will still have degree D, right? Because every edge was replaced by a matching. So this matching gives a degree of 1. This matching gives a degree of 1. So it's still true that locally around every vertex, you see the same picture that you saw before you did it. And this is the property of a topological cover in general. In general, when you have a topological space, a cover of it is something that if you look around a neighborhood around a point, in a small open neighborhood around a point, in the cover, you will see something that is the same as what you see in the base graph. So for simplicial complexes, the small neighborhood around the vertex is just the link. So what is a link? So for a vertex in my complex, the link, I'll call it X sub V, is the link. It's just the neighborhood around V, but now we don't only look at which vertices are the neighbors of V, we also look at the higher dimensional faces. So if a vertex participates in a triangle, then we kind of see that. So it is, what we get is actually a graph if we're in a two-dimensional complex. We have a graph such that the vertices, we call them x v0, are all the neighbors v. And then the edges of this graph are all the edges UW such that UWV is a triangle. Sorry about that wrong order. But you see the picture, you have a vertex V in the entire complex X and it has some neighbors, then some of these neighbors are also participating in triangles. And so when I look at the link, I'm basically looking at, the complex is much bigger. So I'm really looking at this kind of small neighborhood around V, and this is the link. It has these vertices. And then whenever I had a triangle, now I have an edge in the link. Right, so this is like U and this is W, and you have an edge between U and W because there was a triangle. And if there was some other vertex here that did not have a triangle with these guys, then it's now an isolated vertex in the link. Okay, so if I want to define a cover of a simplicial complex, I can try to say, okay, let me continue the way I did with a graph and just replace every edge by replace every vertex by some number of vertices and replace every edge by some matching. But then something that can happen is that if I had a triangle in my original graph, now I replace, so let me try it again here. So I replace every vertex by two vertices, say I'm doing a two cover. Now I can, replace this edge by, try to do it with the same angle. Okay, so I can replace this edge by this matching. And then maybe this edge I can replace by, I don't know, some other matching, like this. But then the third matching, there's one way that I will do it so that I get two different triangles, but then there's the other way that I can do it. And what I'm going to get is a 6 cycle. So kind of this loop of length 3 opened up into a loop of length 6. And this can happen. So in a cover, when this was a triangle in my complex, this is something we don't want. Why don't we want it? Because we want that links of vertices in the base complex kind of are isomorphic to links of vertices in the covering complex. This is kind of the property of being a topological cover, that locally you have this isomorphism. So if I look at the link of this vertex now, it has two neighbors, this guy and this guy, and they don't have an edge. So the link of this vertex is just the empty graph on two vertices. Whereas the link of its covered vertex, so this was like X and this is X prime and X double prime. The link of X didn't look like this. It actually looked like two vertices with an edge. So I want links to be maintained. So I must force that every triangle maps to two triangles. I'm not going to allow a triangle to map to a 6 cycle. Okay, so that's the condition that we're going to require. Let me write it. So a map from, okay, let me not write it as the map yet. Let me just say Y is a cover of X if y0, y1. So let me emphasize that when we have a simplicial complex, we call y0 the vertices, y1 the edges, and y2 the triangles. So this v is like x0, e is like x1, t is x2. And then if we have more dimensions, just keep going. And so a cover, this part of the cover is just one skeleton, it's just a graph. So I want this to be, let's call it lift of the graph x0, x1. Okay, so it certainly must be a cover in the usual sense of graphs. But then we have this extra condition, and triangles must, well, let's say triangles go to triangles. Go to the correct way to say it is that the inverse image of a triangle is some few disjoint triangles. Just like the inverse image of a point here is some t points here. The inverse image of an edge here is some t edges here, and the inverse image of a triangle is some t disjoint triangle. Okay, so maybe I should write it this way. Inverse image of vertex or edge or triangle.
Sorry, you now have a simplicial map from like the apps that you're talking about?
Yeah, so, right, so it's like a simplicial, let's write it this way, a simplicial map. P from y to x, such that P inverse of S, if S is a face that's either a vertex, an edge, or a triangle, is T copies of the same thing, vertex, edge, or triangle. Now, if you can ask, okay, if I talk about three-dimensional complexes or higher dimensional complexes, am I going to add more and more restrictions? So it turns out I don't need to add any more restrictions. Once I know this, the rest is kind of taken care of. So let's first see that links are actually now preserved isomorphically. Okay, so if I have a cover y of x, and I look, so let's see. So if I have a cover y of x, right this way. I have here some graph x, and here I have some, I don't know, more complicated cover. And I look at a point x0. Upstairs, maybe this point has some copies. Let's say 3 of them. Now I want to see what does the link of x0 look here and what does it look like over here. Well, I know that if it has degree d downstairs, each of the copies of x will have the same degree d upstairs. And I also know that if there was some triangle here, then this triangle must have come from a triangle upstairs. So you can see immediately that kind of the graph structure that is on the link of this inverse image of x is isomorphic to the graph that we started with. So the links are indeed isomorphic based on that condition. What this means too is that if x participated in some higher dimensional simplex like this, then you would see this exact structure up here because each one of the triangles must exist. So in particular, like there must have been a triangle in the link of x0, and then this triangle must appear in the link of this copy x01. And also, you know, if I drew the other guy, it would also appear. And the third guy, it would also appear. So I can I already have like the skeleton that allows me to put the correct face in Y that I had in X.
Sorry, this is a stupid question, but is this assuming that Y is like a Cleek complex? Like the fact that the edges force the triangle to be there doesn't necessarily mean the triangle is actually in the complex.
It's not a stupid question. Yeah, you're right. That's why I said it allows me to put the structure. What I mean is that if I have a simplicial map that I already took care of the edges closing triangles properly,
This completes a unique.
I can complete it uniquely to a cover of X. I can, of course, do other bad things, but why should I? Okay. All right, so that's simplicial covers. You know, I probably should draw like a picture, but it's kind of hard to draw a picture, so I'm not going to do it. Okay. Okay, now I want to talk about some property testing question. Since I have this underlying structure of a graph cover where I don't have any constraints, I basically, I just, for every vertex, I duplicate it t times, for every edge, I duplicate it t times, like by matchings. This I can always do. And then what I have here is some condition. The condition is every triangle should kind of close up nicely. So it's kind of a local condition. And I can ask, okay, what if I'm given some kind of simplicial map, like a map from Y to X, and I'm already guaranteed that it's a kind of map that every vertex has exactly T pre-images and every edge has exactly T pre-images. So I'm already given this as is, but now maybe it's not true that all the triangles close properly. Maybe like if I recall this picture which we had with the loop, so maybe if there's some triangle for X, when I go up to the copies for Y, maybe it's some weird thing like this that is like a 9. Something didn't close properly, but here it is. Okay, that is a valid simplicial map going from here to here in terms of like every edge is a matching, every vertex moved to 3 vertices, but the triangles didn't close up. Okay, so I'm imagining now I have some kind of a graph lift from Y to X, and I want to know how often.
So this is a cover of the skeleton, but not of the 2-dimensional.
Exactly. So I'm given a cover of the skeleton, and I want to know how bad is it in terms of being a cover of the actual simplicial complex. Like maybe I can do the following simple test. Choose one of the triangles of X at random and look and see whether the pre-image is like a nice 3 copies of triangles, or maybe it's not. Okay, and I can count that and I can say, okay, 99% of the triangles are actually covered properly, but maybe 1% of the triangles, it's not working. So I can call this the triangle test.
For a triangle to be covered properly, it means that all of the triangle above it are triangles.
Okay, that's a great question. And I mean, okay, so you can define it this way or that way, and these correspond to different questions, and both are very interesting. So let's just choose one of them just for the sake of discussion. The triangle test is, okay, choose some triangle in the triangles of X in X2, let me say. We called it also T. And then check if the pre-image, if P inverse of this triangle is three distinct joint triangles. just to follow up on Zeev's question, you can also choose a random triangle for X. So I'm imagining here that X is some big thing and Y is some big thing, and I have this simplicial map going from Y to X, but I only know that it's a cover in the graph sense. So I can choose a triangle for X, and then I can choose a random base point. So choose one of the points of these triangles and go upstairs, say to this one, and see if when I trace the triangle, which is a loop downstairs, if I close the loop or I don't. So here, for example, I wouldn't close the loop. I trace this edge. There's only one way for me to go to here. Then I trace this edge. There's also only one way to go here. Then I trace this edge back and I land in another vertex. So I failed. So one version of the triangle test is to choose a triangle and to see whether there's any base point that fails, and the other is to choose a triangle and a base point and to see whether or not you fail. It's a matter of how you count the amount of failures. Okay, so when we think of property testing, we often have some kind of global property like being a cover, and we want to look at it from a local perspective and say, okay, is there some small test, like the triangle test is a very small test, you only look at a very small part of your object. Is there some small test that if it passes with good probability, so suppose we think of the triangle test as passing with probability 99%, can I conclude from this that I'm actually close to the property? Okay, so the way I defined being a cover, I mean, it's not me that defined it, but the way it is defined is that the triangle test passes with probability 100%. Now I'm asking, okay, what kind of objects pass this test with probability 99%? Okay, if you tell me that you have such a cover and it's a 1 minus epsilon cover in the sense that it passes all but epsilon fraction of these tests, is it close to an actual cover? Okay, so that's kind of the question that we want to ask. Are almost covers in the sense of this test close to actual covers? Actual covers. That's kind of my
So, I just want to make sure I get the test correct. So you're saying pick a random triangle, pick a random vertex in that triangle, and then go to a random inverse. And now you want there to be like, when you trace triangle in here, you want there to be unique inverses on this side to form a triangle? Is that what you want?
There's always going to be a unique way to trace. The question is whether you close the loop or you don't. So when you moved up here, is the preimage of this walk of length 3. So when you have such a cover, you always have pre-images of walks. For any walk here, once you choose a kind of a base point, there's always a unique way. This walk lifts uniquely. The question is whether this walk closes after, you know, the triangle ends or not. So it's clear so far.
How many edge or two simplicities should we think of X as having? Like, should we think of it having theta and Q, two simplicities?
Okay. This point, I'm not thinking of that.
I guess it feels like if you have theta and cubed simplices, then you should be able to do some sort of supersaturation thing.
What's that?
Like, say that there's a large part of the simplex where every triangle is the sum of a lot of, can be expressed as the sum of a lot.
Oh, okay, but you're basically trying to kind of prove such a result when the simplicial complex is dense.
Yeah.
Interesting. Yeah, that might be true. Yeah. Okay, that's an interesting question. I haven't seen it this
But
time.
here we just don't know anything about the number of simplex.
Well, you know, we know positive answer for this for some
Okay.
cases, but yeah, okay, so, yeah. Yeah, okay, we can think about it some more. Just-
Can you think of an analogous question in the graph setting itself, just with two lifts? Maybe you have loops that are two-sided edges, and then you are lifting them.
You
I'm thinking
mean-
if any question like that makes sense just in the two.
I see. So you mean like I have two edges here like this,
Yes.
and I wanna know if, so I lifted this instead of having like a three edges here, I'm gonna have six of them, and I wanna know if they're organized in pairs. Okay, yeah, I guess so. Maybe soon I wanna now move to define a more algebraic way to think about it, and then I cannot think online, but maybe you can, and we can see what that translates to.
But I mean, you don't need this to be simplistic. Like you can take any polygonal complex, for example, you just decide which cycles you call faces. And then you can, these are the things that you want, like the loops that you want not opened up when you lift, then you can always ask him. Suppose most of the loops don't open up, what happened? Like,
Right, so I see. So what Yotam's saying is, for any pair like this, we're gonna fill this in the face. If you don't like a face of two edges, you can pretend there was some fake vertex here. It'd be a triangle, and then it would correspond to the same question. But I don't know if this is an interesting-
A very interesting constraint somehow, right? I mean, I don't think it's hard to understand what happened with this kind of.
Yeah, I think you'll be able to fix it locally without affecting anything else. Like, what makes a CSP interesting? It's that, okay, I have an approximate cover, and this triangle is actually a bad example, right? Forget about this extra thing. So now I'm gonna just fix it, right? But then I fixed it and I took care of this triangle, but there's some other triangle on this edge that maybe was good, but now since I changed the permutation, maybe I ruined it. But in Shashank's example, kind of the fixing is local and the problem is local, so once you fixed it, you're done. You see the point? I think. Okay, we can talk about it afterwards, so. Okay, so that's our question.
Being close to a cover meaning, if it's not dense, right, well, what's your like distance?
I mean, let's say you're gonna measure how many triangles, edges and vertices you had to. You mean, you want to measure edges separately?
Is it regular or something that's?
I mean, since I'm kind of forcing the map to already be like a T cover, I don't know, T can be N, but. So the only game is like, I guess in the triangles, so. Yeah, let's count triangles, I don't know.
if you just count how many, right, you have like these matchings that you need to take, so you can maybe count how many matchings you need to change into. Like from this like almost cover to actually make it an honest cover.
Changing a matching is like one distance, one matching.
So yeah, you can either count this as one, or you can count like the distance between two matchings, like number of edges you change. These, I think you can measure it however you.
I probably should think of the graph as much larger than the number of sheets, right?
If that's how I think of it, but there is this version where you only, your test is like choose a triangle and then choose a base point, and then sometimes the number of sheets actually grows as well, so. But for now, let's think of the graph as bigger, that way I'll have less mistakes. Okay, so let me focus for a minute on two covers just because it's much simpler, and then we'll generalize again. So when I have a two cover, I can think of the following thing. Here's my X, okay, vertices and edge and so on. And then here's my two cover Y, and basically I have, for every vertex here, I have two copies, right? So I can just draw the vertices of Y as just two copies of the vertex set X. One of them is like the 0 copy and one of them is the 1 copy. Okay, and now whenever I have an edge from U to V, so this is U0, this is U1, so there's these 4 vertices. I can either draw the edge this way or I can draw the edge this way. That's my 2 options. You can see that if it's a 3 cover, then there's more than 2 options. 2 is nice. Okay, so and if I have a triangle UVW, then again, you know, I can draw the first edge this way, the second edge this way, but then the third edge is forced, right? I'm not allowed to draw it crossing because I need to close 2 triangles here, right? So you can see immediately that I can, if I cross once, I need to cross again so that the triangle will close. Right, so really the number of times I have a crossing edge on my triangle is even. That's the condition for a cover to be good. So in fact, I can tell you what my cover is just by telling you for every edge of X, whether I put an edge that respects this partition or whether I cross this partition. So let me put a 0 if I respected the partition and a 1 if I do not respect the partition. So now a 2 cover corresponds to just a labeling of the edges by 0s and 1s. So it's like F2 to the E is a let's say that's a lift. Okay, it's not a cover because it's for now I didn't say whether or not triangles close properly. So this sometimes we call a 1 chain because it's like for every edge, that's the 1, we just put a label. It's this label, for now we put it in F2, later on it will be in a more general group, permutation group. Okay, so for every edge, I just tell you which of the 2 permutations I'm putting. 0 will be this one and 1 will be this one. And then you see that the condition of being a valid 2 cover is that for every triangle, the sum of the labels is 0, 1, 2. Okay, so basically what I want is that for every, okay, so a lift is some function f in F2 to the E, and for every triangle UVW in T, I need f of UV plus f of VW plus f of W U to V0 mod 2. Well, okay, we're over 2. Okay. So that's the condition of being a 2 cover. And here you see it's a nice linear condition. There is some linear map such that if F is in the kernel of this linear map, we are good. Okay, that's nice. Now, one natural thing that people like to ask when they see some object, you know, okay, I have my graph, and what are all the possible 2 coverings of this graph? All the possible valid 2 coverings of this graph. So, of course, when I try to count them or to understand them, I don't want to do double counting or to count like the same object twice. So one thing that you can see is that if I have some cover given by this sequence of 0s and 1s, what happens if I relabel and I just, you know, I take these 2 vertices, u comma 0 and u comma 1, and I just change their location. Okay, and kind of, you know, change all, I don't change anything in the graph, just change the way I draw them on the board. Okay, suddenly an edge that was a 0 would become a 1, right? Because it's crossing all of a sudden. And so kind of, let's see how that looks algebraically. Basically, when I change the location, flip the locations of the 2 copies of U, what am I doing to all the edges touching U? Every edge that was a 1, I flip to a 0, and every edge that was a 0, I flip to a 1. So basically what I'm doing is I'm adding this function. So I have this function that is, I don't know, I have this function, let me call it G sub U. It's a function, in F2 to the E. And this guy is just G sub U for every UV, for every neighbor of U. It's 1, and G sub U for any other edge, I don't know, VW is 0. Okay, so it's basically just like indicates a star around you. And what we did to our F is that instead of F, we defined F prime, which is F plus GU. And notice that when we did that, we can ask, well, if F was a good cover, satisfied all the triangle constraints, what happens with F prime? And you see by the fact that GU just represents flipping the order, you see that indeed GU itself is a function that satisfies these conditions, right? Because if you have a star, then on every triangle, either the triangle involves this vertex and then you have 2 of the edges being 1, or the triangle, doesn't involve this vertex and then everything is 0. So certainly GU satisfies all the triangle equations. And therefore F prime also satisfies all the triangle equations. So in other words, when we have a cover F and we move to this F prime by flipping the location of U, we move to another valid cover, that's fine. But somehow I don't want to count these as different covers. And what's going on here is that the difference between F and F prime was in a function that only depended on the location of U, and this is captured by this notion of the coboundaries of U. So basically, in fact, for any, let me write it this way. For any G in F2 to the V, so now I'm not going to flip just the location of U, I'm flipping a bunch of vertices. So G is going to tell me it's going to be 1s on all the vertices that I'm changing and 0s on all the other vertices. I can look at the delta 0 of G is the function that is defined on every edge to be G of U plus G of V. So this is a definition. Delta is an operator that moves me from functions on V to functions on edges. Okay, so if I have a labeling of the vertices, I apply delta, I get a labeling of the edges, which is just this. And you see that if G was the string that is 1 on just one vertex, then delta G would just be the star. You just turn on all the edges touching that vertex and nothing else. And you can also see that no matter what G was, delta G is a function that if you evaluate it on a triangle, you'll have delta G of UV plus delta G VW plus delta G. You'll get 0 because this is G of U plus G of V. And this is G of V plus G of W, and this is G of W plus G of U. Everything appears twice and cancels. And this is because the characteristic was 2, but in general, you can orient the edges so that it's always gonna work. So the upshot of this is that if I have some cover F, I can always add to it some delta G, which means that I'm just flipping the order of some of the vertices, and I'm still going to have a valid cover, and it's really the same cover. So we're not going to count these as different ones. So really the different covers are the different cosets with respect to all the guys that come from G. So these are called boundaries. So we define V0 to be the image of delta 0. This is since delta 0 goes to the one change, the functions on the edges, V0 is a subset or a subgroup, or in our case here, it's actually a subspace of all the one chains. It's those that really come from vertices. And then we define Z0, these are the cocycles. These are the one chains that satisfy all the triangle constraints. And I can describe the triangle constraints by another map, which I'll do now. So let's see one. And delta one. So just like I have delta zero that maps from functions on the vertices to functions on the edges, let me actually write it this way. Write delta zero here. I also have another coboundary map that moves me to functions on the triangles. How would I define delta one? So now I need to say for any function, if f is some element, some one chain, delta one of f, now I need to evaluate it on a triangle, is defined to be f of v plus f of vw plus f of w. Just the same thing here. So basically, I have these maps. This map moves me from zero chains to functions on the vertices to functions. And this map moves me from one chains to two chains, from functions on the edges to functions on the triangles. And it's just by adding the elements. And now, of course, valid covers correspond exactly to the kernel of delta one. Okay, and this is Z1, and these are called, let me also write, these are called cocycles. And these are called coboundaries. And we have seen here that B0 is contained in Z1, namely, so B0 is contained in Z1, sorry about that. Namely, when you chain these two maps, delta one and delta zero, you get zero. Maybe I can also say what happens when we move to not two covers, but more general T covers.
In general, there's always the trivial cover, and this might, right, when you just have two copies, and then this, if there's no cohomology with it, that's the only one.
Oh, okay, maybe that's a better thing to say now. Okay, so okay, good. Let me talk about that a bit. So what we have there, this delta zero, delta one, this is like a chain of linear maps. So just like a simplicial complex is like a higher dimensional graph, this is like a higher dimensional linear map. And you can ask about, so something that's very interesting, and we already saw it kind of in a more geometrical way, is the quotient of these two spaces, Z1 and V0, meaning if I already have an element here in Z1, I can add to it any element in B0, and it's not really interesting. It's just relabeling of the vertices. So really what I'm interested in is the quotient between these two things. This is H1, which is V1 divided by V0. It's like here it's a subspace. So more generally, it's a group. So it's just the cosets of B0. Everyone is okay with this? And now what the F said is sometimes B0 is actually equal to Z1. Like in the case that Maya was saying, you know, when the graph is pretty dense, it's very hard to satisfy all the triangle constraints. You're not going to be able to satisfy all of them. The only assignment that satisfies them is the zero assignment, but that's false because any coboundary will also satisfy it. So you can always take the zero assignment and now flip some location. So that what does that correspond to in terms of covers? It corresponds to taking the graph or the simplicial complex X and just putting two copies here, disconnected. So all the edges, this is the zero assignment. All the edges are like staying within each of the copies. So you just took X and you put 2 copies of it. And of course, now you can flip the names of some vertices, so maybe when you look at it at first sight, it looks like Y is connected, but really Y is disconnected, it's just 2 different copies. So that corresponds to the first homology being just 0. Okay, it means that there's no non-trivial cover. All the elements here are like the non-trivial elements of Z1 that don't come from like silly reasons. Okay. What else? Let's see. So I'm actually not going to talk about today. There's okay, in past few years, there's been a lot of work kind of using this to create like error correcting codes, classical ones that are LTCs or quantum codes. And there's a way to generalize this definition of a co-boundary map to also allow local coefficient spaces. And then when you define these things, people are like, what is this definition and where does it come from? And I feel like when you describe it in terms of covers, you kind of see it with your eyes. It's kind of intuitive. So maybe that's one kind of, one way to understand it a little bit. Although you can see that working with these things, looking at this object is very complicated, whereas looking at the algebra is sometimes more convenient. Okay.
So when you ask if a almost cover is close to an actual cover, is this usually when there's only one cover? Or like in this case, when there's only the trivial, or you can ask it.
Not at all. So okay, so now that I want to translate this question on covers, it's a syntactic translation. I want to translate it to a question on cocycles. Okay, so we basically said now that every cover gives rise to a cocycle. The converse is also true. Every cocycle gives rise to a cover. Should I maybe say just a couple words on how to generalize it to a T cover? Okay, I'll say that and then continue with the main property testing question. So just to say that when I have here more copies, say 3 of them, okay, so 0, 1, 2. Then really what I need to know, if I want to know how to lift an edge upstairs, what I need to know is just a permutation on 3 elements. Okay, so really to tell me a cover, what you need to tell me is not a function from F2 from E to F2, but rather a function from E to S3 in this case. Or maybe there's a more restricted group that acts on 3 elements like the cyclic group, and maybe you're only going to allow me matchings from that group. That's also valid. So you're gonna ask me for a function that tells me for every edge some element in some group. Okay, so that's more general, like change with respect to group coefficients. And we can also usually, almost always when people think about cohomology, they think of the coefficients as being from an abelian group. But we can actually, in this case, think of any general group. It doesn't have to be abelian, but then this won't make sense anymore. What will make sense is this triangle constraint. You want to say that when you follow the path of a triangle, like you follow this permutation and then this permutation, it's the same as if you followed that permutation. Because I think I shouldn't even write it. I guess I can say that, you know, now I have my F is a function from the edges to some G, some maybe non-billion abelian group. Doesn't have, it can be abelian, but let's not assume it. And then F is a cocycle, so F is said to belong to Z1 of our complex with this G. If I want that, well, I can define this delta, which is basically to follow the triangle and to see that I got the identity. So I do like F of, I guess this is UVW, So I guess f of WU, circle f of VW, circle f of UV needs to be the identity. So I'm basically saying when I follow the permutation around the triangle, I get back the identity permutation. Okay, so I'm not putting too much emphasis on this. Just want you to know that there's a natural way to generalize this. And there's a natural correspondence between cocycles with respect to general groups and covers. Okay.
Is the image of the B0 is still there? I mean, there's the like.
Yes, and the image of B0 is still corresponding to, so what would be, so this is like one chain. What would be a zero chain? A zero chain is to label every vertex by a permutation, which corresponds to changing the names of the vertex on a fiber. This is called a fiber above a vertex.
And it matters what order you do it in. It's not just flipping things, right?
I mean, it's not just, I mean, so you apply some permutation. There's some issue with conjugation.
To be the inverse of VU or something, but that's.
Is that what you meant though?
Yeah, it's not it's a subspace, like a portion of.
It's not a subspace. Now you're complicating me. It's not a subspace anymore. Okay, I'm not an expert here, so it will be, I mean, we can figure it out, but let's not do it. Okay, so I want, before we take a break, so I want to, just before the break, translate the question of, the triangle test and being almost close to an actual cover to the language of this cocycle expansion. Right, so this is my, okay, so we did covers, we did cocycles and covers. I want to do cocycle expansion. Okay, so maybe you already heard that in this high-dimensional expansion, there are these two types of expansion. One is the spectral kind, which is somehow much more easy to understand. And then there is this cocycle expansion, which we're trying to look at from this cover perspective. Oh, wait, maybe I shouldn't have erased the main question. No, it's okay. Okay. Okay, so I have this chain of maps. I just do it again. So I have this C0, and then I have delta 0, C1, and I have delta 1, C2. And my question lies on C1. I'm given some element here. So this is a one chain. It's a function from the edges to some coefficient space, say F2. So I'm still in F2. So C0 here, I'm talking about F2. Sorry. So still two covers. And I'm given a potential two covers. So I'm given some bunch of matching per edge, like a two matching per edge. And I want to know if it's close to being a cover. So this is like, when you give me this thing, it's as if you gave me some assignment of zeros and ones to the edges. And what is my triangle test? My triangle test is this linear equation, which we wrote over here. F of uv plus f of vw plus f of wu, is it equal to 0? Okay, so if I know that my equation passes with 99% probability, it's as if I know that delta 1 of f, the weight of delta 1 of f is exactly proportional to the fraction of, let's say, good triangles. Yes, good, bad, one of those.
like triangles that don't,
Right, the bad ones are the ones that don't close up to a triangle, right? Because it's these, what is delta one of f? Delta one of f is a two chain, so it labels every triangle by 0 or 1. And how does it label a triangle? By adding up the values on the edges of the triangle. So it's the fraction of triangles where this doesn't add up to 0 mod 2. So you have an uneven number of crossings and then you don't line up, okay? So what is my question? My question, are almost covers close to actual covers, is the same as asking, if I know that the weight of delta one is small, so like epsilon, does it mean that there is some f prime that is close to my f and it is actually an honest cover? So
is this wave function computed only on the two simplices of x?
right, so the weight of, okay, let me just define it. This is okay, this is just defined to be this is just a Hamming distance, a Hamming.
So this then corresponds to Tom's earlier suggestion of measuring distance by how many of the crossings here changing. Since flipping one thing on F is changing how you're doing the matching above, right?
I mean, this is actually Hamming weight on triangle, so it's not.
Oh,
Okay. Yeah, let's get back to that question after the break, and I have a minute to think about it. So, so I'm just counting for every triangle, which triangles, these are the triangles in the base space. So for every triangle in the base space, I'm seeing whether the thing closes up. And there's two variants to how I compute this. Over F2, there's only really one way to compute it. If the coefficients are from a larger group, then I can factor into the weight. For every triangle, you kind of follow the three permutations and you get some new permutation on your original point, and you can ask how close it is to the identity. So then if you can either say, well, if it's not the identity, I put a 1, if it's the identity, I put a 0, that's one way, or you can be more subtle and say, okay, how far is it from the identity, and factor that in. So the second version corresponds to these questions on stability. Maybe you remember that Michael talked about them. Probably we'll talk more, where you look at these like almost homomorphisms, where you do like, you follow the first permutation and the second permutation, or you follow kind of the other edge, and you want to know how close did these two things come together. Okay, so let's stick to two covers. So here it's easy to define. And so on one hand, we have the weight of delta 1, and on the other hand, we have the distance. Again, this is Hamming distance, but now I'm going to talk about the distance of F, so it's going to be Hamming distance on x1. Okay, I'm going to weight all the edges the same and all the triangles uniformly. The distance of F1 to F to Z1, meaning I was given some arbitrary F, and I want to know how close it is to valid covers. Z1 are the ones that are good covers. So what I want to know is whether, if the weight is small here, only a few triangles failed, does it mean that I'm actually close to a valid cover? Okay, and that's exactly the notion of Cocycle expansion. It's comparing the weight of delta 1 to how close you are to actually satisfying, to being in the kernel of delta 1. And so we define this, we define the Cocycle expansion constant, H, to be the minimum of this ratio over all F's that are not in Z1 of this ratio, the weight of delta one of F to the distance of F to B to Z1.
B1 is not,
B0. So,
zero is not.
so this is cocycle expansion. And all these things are the same. You can, when Z1 is actually equal to B0, we can, we call it coboundary expansion. But it's the same object. Okay, so you can ask for a given X, whether this H is bounded from below, it's like a constant. If it is, suppose it's some constant, then you can say that when the weight is small, it implies that the distance is small, right? Because for any F, this ratio is bigger than this minimal ratio by definition. And so when this is at most epsilon, the distance is at most H times, epsilon divided by H. Okay, so we're kind of interested, a graph or a complex is a cocycle expander when this ratio is lower bounded. And this means if you have a cocycle expander, it means that whenever you have an approximate cover, you can fix it to be an actual cover. And yeah, okay.
So for graphs, it's always kind of, if it's connected, right, there's always coboundary. There's no cocycles are interesting because if the graph is connected, Z1 is always B0. Right?
Okay, so maybe I should also talk about cocycle or coboundary expansion one level below.
If the graph is connected, right, there's no non-trivial.
There is. Like B0 always corresponds to like covers that are disjoint copies. And so a graph you don't have any triangles, so like any function is in Z1. Right, because you don't have any tests, like any triangle, there's no triangles that you're testing for. But only the disjoint ones correspond to B0.
So but for graphs, you look at the one level below, you go from the empty sets
Looking
to
at delta
one.
zero delta.
Yeah, like the coboundary, like the regular, like the trigger count, if you move this one down, it's the trigger count.
Let's talk about zero cocycle expansion.
But there's no, it's connected, so coboundary to cycles.
Yeah, so the upshot of this is that one cocycle expansion, meaning when we talk about one chains, corresponds exactly to cover stability, to having the property that when you have an approximate cover, you're close to an actual cover. What is zero cocycle expansion or coboundary expansion? This corresponds exactly to edge expansion. So let's see that. So here we look at delta zero and we ask ourselves, what if we have, instead of having a function here, we have a function here. So it's a 0-1 labeling of the vertices, which is just like a subset of the graph. And we ask, well, what if delta zero of it has very small weight? What does that mean for a function to have delta zero very small weight? Delta zero adds the values of two edges. So delta zero of a function is exactly one on all the edges kind of going from the set to the complement. If a function is one on some set, zero on the complement, delta zero will exactly light up on all the edges crossing the boundary, and it will be zero inside the set and zero outside the set. So delta zero having small weight exactly corresponds to a set having small boundary. Okay? So what do we know if a set has small boundary? We want to say, is it close to a set that has zero boundary? Okay, what is a set that has zero boundary? That's exactly the kernel of delta zero, right? We want to know if a set has small boundary, is it close to a set that has zero boundary? So we define this H, I guess I can call this H1, and then that will be H0, can be the minimum over all the functions that are not in Z0. So these are functions that delta zero of F is not zero, okay? Meaning these are functions that have some boundary, And then we can minimize the weight of delta 0 of f, delta 0 of f to the distance of f from the kernel of delta 0, which is the functions with 0 boundary. Now imagine the graph is connected. Suppose the graph is connected. What does it mean to be a set with 0 boundary? It's a constant function, right? All zeros are all ones. So this set is just two elements, the all zeros and the all ones, right? So what is the distance of f from this? Well, f itself, here's the graph. F itself is some 0, 1 function. Suppose it's 1 here and 0 here. Then its distance from this is exactly the size of the smaller part. If f was 0 here and 1 here, the distance would be obtained by this guy, and again, it would be the size of the smaller part. So this denominator is exactly the minimum between, s and s complement. If we think of s as being the ones of our function, and here we will have just the number of edges crossing from s to s complement. The edges crossing from s to s complement, and here we take the minimum over S naught and T, or S naught, the complete, right? So we just don't allow these two kind of 0 boundary things. And this is exactly of expansion. So that was related to it?
Yes, so there's no, if the graph is connected, there's no cocycle. I mean, there's nothing interesting there, right? It's only the trivial. So.
Yeah, I mean, right. If the graph is not connected, then there's more, right? Then on every component you can have a different constant. But I'm not getting into that. So in that sense, you see that it's like a high-dimensional expansion, right? Because the 0 version was our beloved edge expansion, and then the 1 version, you can just kind of syntactically define it, because all this, these coboundary maps have been studied for centuries or something, and so you can just define it syntactically, but then it's hard to understand what they mean, and looking at covers is one way to understand them, and there might be others. Okay. Just want to say that, what is a graph that's not an expander, like a cycle, right? It's a very good non-expander. And you can see that it doesn't satisfy a constant lower bound on H0, right? Because you can have this function that is ones on all this part and zeros on all this part. So it only violates, one edge here and one edge there. But it's very far from any function that's a constant in the entire graph. So certainly this quotient, it can be very small. It can go to 0 with the size of the graph. Here it's less easy for me to give an example, but maybe Tom can come up with something. I don't know. Anyway, you can come up with examples, but once you go to higher dimensions, it's hard to envision it. Exactly.
Or like tiling triangles on a sphere or something. Maybe that's still not that easy.
You want to give an example for something that's an approximate cover, but not a cover. But cannot be fixed.
Just to show each one can also vanish, like the cut is.
Okay, all right. Okay, so I just, before we take a break, I did want to mention something interesting about, so in the second part, I want to talk about agreement tests and how they relate to covers. But before that, I wanted to mention something about the relationship to spectral expansion. Should I do it after the break? How tired are you? Should we take a break first? Okay, so I'm doing it. Okay, so spectral expansion. High-dimensional expansion. So let me not put too much time into this. I just want to say that one way to define spectral high dimensional expansion is to say we want a graph such that a complex such that x0, x1, the underlying graph, is a spectral expander. Meaning that the second largest eigenvalue normalized is bounded by lambda. And I normalize because I want the eigenvalues to be between plus and minus 1, not to take care of the degree. And I also want that for every vertex v, if I look at the link graph, so xv0, xv1, so even if my high dimensional expander had constant regularity, so every vertex participated only in 100 edges. So this graph is going to be a graph on 100 vertices. Still makes sense to ask whether it's a lambda expander or not, and we want this to also be a lambda expander. This looks like a very different definition from that definition, but we do know that for the case of zero expansion, so when you don't have this extra condition, you just require something about the spectrum of your graph, miraculously, it exactly kind of captures the same qualitative behavior as this edge expansion. So it's like you change, what is spectral expansion? It's like you're labeling your vertices not by 0, 1s, but by real values. And somehow there's a rounding thing that you can do, improve what we call Cheever's inequality. And there's a relationship. So is there a relationship between spectral high dimensional expansion and cocycle high dimensional expansion? And so there is this nice counterexample that I wanted to just show you and to ask whether it can be overcome. So I feel like there should be some positive statement relating these two, but so here's a counterexample that obstructs such a statement.
Counterexample to which direction?
So this is a result of Wagner and Gundels, I guess. Wagner says there exists there is a 2D complex that is a lambda HDX, but H1 is like very small. So, okay, I'm not writing parameters for lambda being some constant, but the cocycle expansion vanishes. And what is this example? It's a random complex. So here's the construction. So let x0 be some set of n variables, so n vertices. x1 will be the complete graph. So we put the one skeleton to be everything. And now we just need to say which triangles we add. So x2, so it's a random complex. x2 is going to be each triangle. I want to write each triangle is added independently with probability p. That's a random complex. Maybe I should say this whole definition of cocycle expansion was introduced by Liniel and Meshulam, who studied random complexes and studied what their behavior is with respect to this definition. And it was also independently studied by Gromov, who looked at some other topological overlapping property. It's very interesting, but I'm not going to talk about it today. So I want to say each triangle is chosen independently, but instead I'm first going to say choose at random. So I'm going to do this. Choose some f at random, just a chain on the edges, uniformly at random. And then you're going to choose each triangle is in with probability p, as long as doesn't violate f. So what I mean, by this is that we want F to be in the cohomology. So we want to make sure that when we sum F along that triangle, you get a 0. Okay, so, sometimes it will be and sometimes it won't. And then finally, we add some more triangles, and then this is step 1. And step 2, we add some more triangles. So each triangle is added with probability Q. Sorry. Some much smaller Q. The point of the last step is to, okay, we'll see in a minute. Okay, so this is the construction. First, you add a lot of triangles, but make sure that F is not violated, and then you add some more triangles that will actually violate F. Okay.
So pick your constants.
I don't remember. Probably it's enough to do like so that the average degree is log n or something like that.
You can even take P to be 1. Like you can just add all the triangles, and you can instead take Q to just add like one extra triangle that violates F or something. This is also one.
Okay, let's try Altan's version. So what I want to see first is how does this graph behave with respect to spectral HDX? And then what does it behave with respect to the other kind? And with respect to spectral HDX, I'm actually not gonna, well, this is a complete graph, so there's nothing to say here, it's an expander. Here, I just need to look at every link and see what's going on. But when I look at the link, then what do I have here? Well, the neighbors of a vertex are all the neighbors, right? And then I drew them in two clouds because I'm thinking from the vertex to all of these guys, that's where F equals 0. And from V to all these guys, that's where F equals 1. And since F was chosen randomly, they're probably roughly evenly distributed. And now when I want to add a triangle, well, if I want to add, for example, this triangle, I'm gonna be able to do it if this edge was a 1, right? Because I need to have an even number of 1s. Well, but imagine that you first kind of choose the triangle and you say, I want to add it, and then you choose F on that edge. So it's as if you chose the triangle with probability P times a half. So basically you need P over 2 to be enough so that this random, and the same thing, if I want this edge, I need F to be, I don't know, 0. Again, this happens with the F. So, what I'm doing here is I'm choosing a completely random graph on this vertex, and I just choose P to be large enough so that this is an expander with high probability. So this construction gives them a spectral HDX. And it's like okay, that's clear, right? Or not so clear? Not so clear?
F was chosen randomly.
Yes.
Randomly.
Okay, and now I want to know what happens with respect to the cocycle expansion. So imagine that you have any okay, what do I need to prove here? I want to say that there is some F that achieves very small, violates very few triangles. So I'm going to choose my F, right? By choice, this F violates only the triangles that were chosen in the second step. So Yotam actually suggested to only add 1, so it violates only 1. On the other hand, I want to show that it's far from any valid F. So, well, now you need to understand that when you chose all these triangles at random, you basically didn't leave any valid Fs alive. Everything died. And your F, because it was chosen randomly, it's also far from any co-boundary. So the only kind of solutions that will satisfy all the triangles will be co-boundaries, like the 0 solution plus changing vertices. But then F, since it was chosen uniformly at random, it's very far from like a cut. Okay, so did this kind of planted solution complex where you planted F, but then you also ruined F just enough so that the graph is still a very good spectral expander, but somehow the cocycle property was killed. Yeah, and I wonder whether, I don't know, whether anything can be done to salvage this.
But the construction of HDXs with constant degree are very not random. They're very like special.
Right.
So could be that it's true for those, for the constant degree.
Yes, so, okay. I didn't say anything about like what we know. Yeah, for those HDXs that we know and are spectral HDXs, we usually, or almost always, we know that they're also coboundary expanders. Then, of course, you can ask, you know, how does this constant depend on the parameters? So these HDXs often come with some underlying group and there's like an underlying field, and then you can ask what's the dependence on the field and on the dimension. And there's been a lot of work on that. And actually, this will be very important after the break when we talk about agreement tests. Kind of
Do you mean they're mostly cocycle expanders, or you actually mean they're mostly coboundary expanders?
it's the same, right?
No, a lot of them don't have anything.
Yeah, so according to my definition of cocycle expander, you know, it's having to do with being in Z1. If Z1 happens to be equal to B0, that's great.
Sure. You said coboundary expansion.
I intermix these two terms because I don't see the difference between them. The difference between them is only whether or not the cohomology is zero or not. So that's kind of an independent question. Okay, so let's take a break and then I can talk about the last part about this application to agreement tests. Okay, so I'm not going to introduce the whole topic. I just give you a couple of examples to see what the motivation is. When we have a low degree function, these are like in PCP theorems and so on. We sometimes want to test, is it low degree? You know, is there some polynomial in m variables? So suppose this is a large field FQ. Is there some polynomial in m variables such that the degree of f is much smaller than q? And okay, there are these natural tests you can do, like pass a random affine line and then read some d+2 points on that line and check if what you see there agrees with the low degree function. But if the degree is low but not that low, it means you need to read many queries, O of D queries. And in PCP, sometimes you want the number of queries to be as small as possible, like 2. And then the natural thing to do is to ask for the input to be given to you in a better way, in a way that allows you to make only 2 queries. And the better way is you ask F to be given to you by restrictions. So we want to have a restriction of F restricted to, say, a line for all.
This is seemingly a new subject, not related
New
to
subject.
previous.
Yeah, it will be related, but yeah, it's a new subject. So we are asking like for the input to be given to us in this form. Of course, what we are given is for every line something. It's not promised to be the restriction of a global F. And we want to be able to test that our bunch of restrictions actually came from one global thing. So the question is, given a collection F sub L for each line, does it come from some global F? So you see how it's also a local to global question, just like the covering, but in very different, seemingly different area. You have a bunch of local pieces and you want to know if they correspond to something global. How are you going to check that? So, usually we think of here as f to the m. We're given, for every line, we're given this f sub l, and since kind of the prover who gave us this information is trying to convince us that it's coming from some global low degree function. So for sure, the prover is going to give us a function that's locally low degree. So here I'm going to get a low degree function univariate, and here I'm going to get another
How
one.
do you think about the parameters Q and L?
Let's think of them as being roughly equal and large and going to infinity. So then they're both logarithmic, like if the input size is like fq to the m. Okay, so for every line I get some low degree function. The degree is also like q over 100 or something related to q. I get a low degree function, and how am I going to check that all these come from one global function? Natural thing to do is to do a line versus line test or a line versus point test, where you take two lines that intersect in some point and you check that the local pieces agree on that. So this has been very well studied. There's a lot of papers.
Anything about the limit under those steps?
So the game is like this. The prover gives you what we call a lines table. For every line, the prover gives you, d+1 coefficients that describe a degree d function. And then your test is you choose two random lines that intersect, and you evaluate, you turn these d+1 coefficients into a low degree function. You evaluate at this point from this side, you evaluate at that point from this side, you check that they agree. You do something. Okay. Now, you can do line versus point. You can also ask the prover to give you like the point evaluation, and then you do a line versus point. This is a line versus line. There's also a plane versus plane, where instead of lines, you're asking for a planes table. And basically for every two-dimensional affine space, which I'm going to call a plane, you're given a bivariate low degree function, and then you choose two planes that intersect on the same line, and you check whether the two local functions agree. So you get a bunch of local functions, either parameterized by lines or by planes or by cubes. And there's many, many works on this in trying to understand the correct parameters. Correct parameters means, suppose you know that the line versus line test passes with some probability epsilon. So it means choose L1 and L2 that intersect on a point, and accept if FL1 at X equals FL2 at X. And then kind of the line versus line theorem will tell you, like the theorem will say if the success of the test, so the success is really given by the table of values you got. If the success is bigger than some alpha, then you want to reach some conclusion about the global structure. Means that there exists some global F that is low degree and agrees with I don't know, some alpha prime of the FLs. This is the kind of theorem we like. Says if the local test agrees, so choosing two local functions and they agree, often there must be a global reason. There must be some big low degree function so that the local functions always kind of, not always, like with some alpha prime probability, they agree with that one global region. Okay, so what kind of alphas do you expect? So the first thing to ask is when this is like 0.99. 1 minus epsilon probability you agree, what's going to happen? And actually, yeah, you can prove that for, this is quite well understood. The second thing you can ask, okay, what if my alpha is actually only epsilon, like small 1%? Is it true that there's always a global function that basically explains all the agreement. And the answer is not exact, right? So what can happen? It can happen that you have, this is your space. You can have two different global functions, F1 and F2. And half of the pieces, either planes or lines, doesn't matter. Half of the pieces, their answer is according to one function, and half of them, the answer is according to the other. And you can decide which one randomly. Still, when you choose a random line and two random planes, say that they are contained, with probability half, they will be both subscribing to the same global reason. And so what you can expect from your theorem is that when the success is small, like 1%, okay, there exists a global function, but this one global function is not going to explain all of the agreement. There's going to be several global functions, what we call a list, such that, anytime there's agreement, it's explained by one of the elements in the list, plus some error. Some agreement can be an error, but actually you can explain 1 minus delta fraction of the agreement by these elements in the list. And this is what we call the list decoding regime. So for like all of the, for the longest time, we actually called the low success probability. So there's two kinds of regimes here: high success probability, 99%, and low success probability, 1%. And for the longest time, we called one of them the unique decoding regime because it corresponds to having a unique global function, and the others the list decoding regime because it corresponds to having a list of global functions. And I want to actually show you kind of a situation where that's not the case. Okay, so this is the low degree test situation, and indeed in the low degree test, we understand in the low acceptance regime we must have a list. And now there's a generalized question that does not have to do with low degree anymore, and it has to do just with representing some global function by its restrictions to a bunch of local subsets. So you can imagine replacing the collection of lines. So instead of this f to the m, now I'm going to draw it like, some squiggly thing. This is some collection of vertices, some points. Okay? And I'm going to want to look at functions on all these points. But instead of asking for, a table of values, one per point, I'm going to ask for a table of restrictions for some subset. So I'm going to have some family of subsets of V. This is called my X. This is subsets of V. For example, you can think of X as being V choose K. So it's like all K element subsets of V. It's one example. And if I want to represent some function F from V to some alphabet, let's say 0, 1, can be larger, I can represent it by this kind of collection of restrictions. So I'm going to have this Fs. It's a function from S to 0, 1 for all S in X. So this is like a collection of local functions, 1 per S. So this is S. And for every S, this table gives me a local function just on S. Okay, just like I got a local function just on the plane. And
How big should I think about this as 3 log?
Yeah, good question. Maybe think of them as like somewhere between, like not 3, like going to infinity, but slowly, even more slowly than log. So like K is 1,000,000 and V is N, something like that. Okay, so I basically have given this and I want to know whether or not this collection came from a global function. Okay, and I want to have a theorem like this. I want to devise a test. The test kind of, the picture shows what the test will be. It will be choose some smaller set, let's call it T, intersection. Choose some smaller set, choose S and S prime that contain this smaller set. I'm not going to write it for you. And accept if F sub S agrees on these T points with F sub S prime. So that's what we call an agreement test. So agreement test. Choose, let me just write like this, S1, S2 that intersect on some T. And accept if Fs1 restricted to T equals Fs2 restricted to T. And kind of the theorem will be if the success of this test is at least some alpha, then there exists some global function f on the vertices, say to 0, 1, such that that agrees with alpha prime of these fs's. So I kind of tried to copy exactly what I wrote here. Here, now I need, there's a, okay, so this is also kind of rather well understood for the case of the complete complex. So you have all possible K-element sets. There's a good amount of work in this, and there's a lot of subtleties, like maybe agrees doesn't mean agrees exactly, but only on most points. Let's not get into it. Okay, and now you can also ask, what happens if you want a more efficient encoding? So in some sense, this is kind of an encoding of F. You had F that the encoding length was, well, one bit per vertex, and you move to a collection that for every K element set, you have a local function. So that's like n to the K. The encoding is very inefficient. The advantage is that you can kind of check this with only 2 queries or maybe 3 queries sometimes, whereas here you kind of need to make more queries if you want to do something without getting into details. So we want the same kind of theorems, these agreement theorems, for much sparser x's. And you see already that if you want it for much sparser x's, you want your x's to somehow cover the space in a good uniform way, but also to have non-trivial intersection. If you're going to choose K element subsets kind of at random, which is a natural first attempt, they will usually intersect on one point at most. Usually they'll be disjoint, but even if you condition on intersecting on one point, they won't intersect on any more. So that's not so good. And it turns out that high-dimensional expanders are exactly kind of useful here because they give you, if your expander is k-dimensional, so you have k element set or k-1 dimensional. You have k element sets, and somehow they overlap in a non-trivial way, and that's useful. You can prove such a test, and indeed for the alpha being 0.99 and x being a lambda HDX, so spectral expander is enough to prove an agreement theorem. Oh, and this was a result that I proved with Tali Kaufman 8 years ago. And then we asked, okay, kind of a lot of the interest in such questions is in the 1% regime. Okay, so this is like, don't really mean these constants, just the fact that the probability is small going to 0. So what happens in the small acceptance regime? So you have a collection. So your collection of subsets is something special. It comes from some HDX. You know that every pair agrees with some probability alpha that's very small. And you want to conclude this list conclusion, that there must be a list of global functions that agree with and explain all of your agreement. And indeed, for the case of the complete complex, this is also an HDX, it's the complete complex, we had already such theorems. Okay. So we conjecture that it's also true here. But somehow it fails, and I want to show you how it fails and how it can be fixed. So let's see what the strategy. Let's kind of try to prove it and see what's going on. So suppose I want to prove that if I have this 1% agreement, there must be some list of global functions. How would I even prove it? I'm given a collection of global functions, they agree some part of the time, and I want to kind of prove that there exists a global solution. Basically, my proof will need to reconstruct this solution. So if my agreement was 99%, maybe the reasonable thing to do was to say, okay, for every point, I look at all the subsets that contain it and take the majority value. And that will give me like a first approximation. Maybe I need to do some more things, and then I need to argue about that. But when the success probability is 1%, you have this problem that, it could be that there's like two different global functions that agree, and if you take majority, you're done. You'll fail. So you should do something else, and the natural thing to do is to do some kind of conditional majority or conditional decoding. You're gonna say, okay, I'm gonna look at so I'm gonna fix some vertex V, and I'm gonna look at all the subsets that contain V. Okay, so in the case of the complete complex, this is really the link of V. You're looking at kind of what the complex looks like when you condition on containing V, and you actually look at what's outside there. So if the complex is the complete complex, what you see here is like n choose k minus 1, which is still very good. But if you're in like an HDX, then all this is like constant degree. It's like a tiny, tiny fraction of the entire complex. Okay, so it's a tiny fraction, but it's still here. And you can say, okay, if the value of V is 0, actually here it's not so good to think of alphabet of just 0 or 1. So we can either think of a larger alphabet, or else I'm going to have to condition on a few vertices, like let's say, T vertices. So I'm going to look at T vertices, much smaller than K, and condition on all the subsets that contain all these T vertices. And now I'm going to say, okay, if the value on these T vertices is all 0, let's look only at the subsets that say all 0 here. Okay, since these guys already agree on T, if they happen to intersect on another point, they're very likely to also agree there. So I'm going to take now, for all the other points, I'm going to take majority condition on agreeing on this prefix. And I'm going to get some assignment to all the vertices in my link. I'm going to get some extension of the zeros to something. And now I'm going to move to the next guy, 0, 0, 0, 1. Now, sometimes, for some strings here, there won't be any subsets that even, or there'll be very few, so I'm going to discard that too. And I'm going to be left with some strings that I started with, and they extend nicely, the majority is well defined. So I'm going to be left with a list of maybe 2 or 7 kind of functions where the majority was nicely defined, and this is going to be a local list. So what I got is a local list of functions on the link. So I moved from having a function just on a single face to having a function like a bit broader, but still kind of local. Okay, and I do it for every kind of T-face separately. For every T-face separately, I get a list. Okay, I get a list. And one way to think about it is that I duplicated this situation multiple times, right? So this was for 0, 0, 0, and this was for 1, 1, 1. And so I had like, for each initial link, I now have several copies corresponding to the different ways I could have extended. Now, if I had another set of T elements that's very adjacent to this one, maybe I removed one vertex and added something else. So now I have a different link here. Okay? But some of the sets are the same because they contain both these T elements and those T elements. So again, I have here some this and that. But somehow, because these sets overlapped, the lists naturally kind of agree with each other. For example, when I assigned all zeros here, maybe this corresponds to this guy. So I can have like a matching between the different elements on this list and the different elements on that list. Okay, so basically what I'm seeing is that I first locally decode in a link, then I get a list of functions, and then for adjacent links, I have some natural way to get a matching between these lists. And these matchings are not perfect, there's errors, sometimes it's not really a matching, it's like an almost matching, because you can see that these decodings can sometimes fail. But it's true that there is some simplicial structure here, and when you have like 3 different key faces that form a triangle, the matchings usually align well, like the triangles close pretty well. So you see, I'm kind of explaining hand-wavingly, but you can see intuitively that something is going on here in this proof approach that naturally gives rise to some kind of approximate cover of your original family of subsets. Does that make sense? Okay. So then, okay, you want to come up with a global list. What you can come up with is some kind of approximate cover. And okay, suppose you said, okay, I'm working on an HDX. I already know that some of them are good Cocycle expanders. So I already know that if I have an approximate cover, I can fix it to be an actual cover. I don't change a lot. So maybe the places I change, I need to fix the function somehow. I don't care. Okay, so now I have a global cover. And now you start to see the problem. What you end up with is not a list of global functions, but rather a cover of your original space and a function on that cover. So on the cover, you have, for every element, you have a value. And so you have a value on the cover. And now when you think about it, actually that can give a counterexample to the theorem. Because imagine the following thing. This was your x here, x, and this was your y, which is like a 2 cover of x, y. So every vertex here has 2 copies here. Now, forget about this for a minute. I'm now constructing a counterexample. So x is here, and I have these k element sets. These are faces. And above every set, I have 2 of them, and so on. And now I want to construct an assignment of local functions to x that agree a lot, but there's no global function to explain them. And what I'm going to do is, for every pair of vertices that cover this guy, I'm going to randomly assign them either 0, 1 or 1, 0. I don't even have to do it randomly. Just think of it this way. So I'm assigning now, here I have n vertices, here I have 2 n vertices. I'm giving a random 2 n bits here. And now for every set, for every face here, I look at the 2 copies and their values. One of them is like 0, 0, 1, 1, 1, and the other is 1, 1, 0, 0, 0. They're actually antipodal. And I'm going to just choose one of them at random and copy it here. Okay, so now if I have, that's it. I define now an assignment of local functions to my x. The problem is that this assignment passes the agreement test quite well. Right? Because if these 2 local functions came from the same copy, and that happens with probability half. If they came from the same copy, I'm going to succeed. So this assignment succeeds with probability alpha equals a half, and yet there is no. Okay, so then to finish the argument, I need to say, well, but there is no way to kind of define from it something global on x. Well, there is one situation where you can define a global function on x, and that also makes sense because I already told you that for x equals v choose k, the theorem actually holds. So how come this counterexample doesn't happen there? So the thing is, maybe what I thought was a counterexample here is actually a global function. Maybe this y, for example, so imagine that this y was actually just two copies of x completely disjoint. That's one possible cover. If that were the case, then this is exactly my list. I have one global function, half the sets agree with that one, and another global function, the other half of the sets agree with that one. So if my cover was a disjoint union of copies of x, I got my list. But if my cover was something, non-trivial, then there is no way to go up. So really the theorem can only hold when this complex X has no non-trivial covers or no almost non-trivial covers. Okay, but if your X has non-trivial covers, the only thing you can expect is like the theorem that we proved with Yotam is that there's always going to be a cover and an assignment to the cover, and that's like our global object. And if it so happens that your complex is simply connected, so there's no non-trivial cover, then this recovers the original statement. Or otherwise, it just gives you a counterexample. Okay.
So if there's no non-trivial covers, then it's true for the low agreement regime, the low alpha?
Yes, and even more than that. Sometimes, like in these HDXs that come from quotients of Brutitz buildings and other quotients, sometimes in that case, there's always going to be covers. But you can you can be in a situation where all the covers have many, many sheets. So there's no small, small covers, like 2 to 1. Okay. So if that's your situation, notice that in this counterexample, since I had 2 copies, I had here probability half. If I have here t copies, I would have probability 1 over t. So if I tell you that the success is at least half, a t cover won't be a counterexample to that. There is some gain here, and that's how these results were proven both with Lubotsky and Yotam, and also Dol Mincer, Noam Lifshitz, and Mitali Bafna proved these results by going to complexes that you can prove that they don't have small covers. And then there's a kind of a game between the alpha for which you prove your agreement test and the, how much you can prevent covers for your complex.
So how much can you, do we know?
We have very bad trade-offs at the moment, and
So which papers are we talking about?
okay, so there's a few papers, some of them just, for this whole approach to work, you need to be able to fix almost cover into a covering. So you need to prove this kind of cocycle expansion for
But I
special
think those that
complexes.
use some kind of limit on how some non-existence of small covers.
Oh, you're asking about which construction? So this is like a paper with Alex that looks at some symplectic version of the building, and Alex does all this magic with profinite groups that gives that. And there's a similar paper with Lifshitz and Mincer and Bafna. Okay. So I guess that's all I wanted to say about this. Just kind of felt that people that do list decoding and often want to do some kind of algorithm that kind of starts locally and then combines things, you always need to be careful that you don't get hit by a cover.
Yeah, actually, I have a related question. Do you think you could prove lower bounds for codes, like not an agreement for a list decoding of, I don't know, certain objects for this type of?
Like codes that we already know?
Yeah, or I don't know, or like if this method, I mean, it proves a lower bound for agreement, can it also?
That's a good idea. Yeah, might be. But we don't usually care about lower bounds for specific codes. We want to find codes and but I mean, it is some kind of a barrier that we need to.
It'd be interesting to know this sort of object can be.
Right, yeah.
I think it's
Yeah, I think it's also interesting to so okay, we talked only about simplicial covers. Of course, you can also talk about other kinds of covers and also, now, if you think of these boundary maps, these deltas, if you make them richer, it's still kind of, there is still some cover underlying it, and yeah, maybe that's also something.
The algebraic tests that you talked about, are there HTXs underlying those objects also?
Are there?
HTXs underlying those objects, like can you build a complex out of that?
Out of which tests?
Like, for example, the line test.
Ah, I see. They're more like not simplicial complexes, but Grassmann complexes. And it's basically, you look at all lines, so it's like the complete Grassmann. It's, you can call it an HDX if you want. And there's also another line of research, Avi and Yotam and Siki were doing, trying to construct specifications of them.
Right.
Okay, so anything